Okay, thanks for attending the last session, or I call it the terminal session in the stream of DevOps sessions available. But they're also parallelized as well, so we need to do a reduce operation in this session. Okay, that's a poor joke, but I had to make it. Okay, so the agenda today, I'm going to talk a bit about streams basics, sort of, let's see, how many people have used Java streams, have been to stream sessions before? Quite a few. Some not, so hopefully there'll be some benefit for those who've seen it before and some bigger benefit for those who have not. Then I'm going to start getting into the parallel game, explaining why you might want to go parallel or why you might not want to go parallel, and how you might decide on what to do there. And then I'll get into what we might do next with streams, both in the near term and the far term, and we'll see how much time we have for that. I'll try and balance things out in terms of that. So the goal, if I can get this across, is for you to sort of build up a mental model of streams, and especially how this model works in parallel, so that you can apply that mental model, and use some sort of rules and heuristics and measurements if you want to decide whether you want to go parallel. The code is here. It's actually Java 1 code because I was, well, not too lazy to update it for DevOps, but I think it's relevant for DevOps too. So what is a stream? It's really just an abstract view over some data. That's it, to perform some operations on sequentially in parallel. That's it. Jose has a nice sort of 7-point bullet which goes into more detail on that, but you can think about it as building up a recipe of stuff you want to do to manipulate data, and then you say go, operate on that data, and it builds up this recipe lazily, then works it all out and can calculate that sequentially or in parallel. What is a stream, a Java 8 stream at the moment? Not really. It's not at the moment a way to consume IO-based events, although we think we can adapt it to consume in a certain way, but it's not RxJava. RxJava is pretty good in what it does. There's some J1 presentation numbers I've linked to there. I think it was talked about in DevOps as well. It's not completable future, so it's not the sort of the reactive you might think if you're thinking reactive in RxJava and a new class in Java 8 completable future there. And it's not a way to richly distribute computation over multiple nodes in a distributed system. There is something called distributed stream. There's actually a paper online. You can go to the links are in the presentation I'll update, which talks about leveraging the Java stream and a distributed stream, so you can distribute your computation over a whole bunch of Hadoop nodes and run your local stream on each node or a coherence cluster or something like that and merge all the results back together again. So there's a way of combining these things, quite interesting, local processing, distributed processing, map reduce in the local or on your own computer and in the large, essentially. So the concept of a stream is larger than the Java 8 stream. So let's get into the basics and get into some very simple code. So what I want to do, first of all, is count up some words. And I have a list of words conveniently available. So what you do is you call stream on the list. Now stream is a method on list, and it didn't exist before. So what is it? Who's shouted out? It's a default method. It's a new method on list. So if we actually look at the code here, it's actually code in the interface, the default method there with stream. If you want to integrate streams into your own data structures and your own collections, look at how it works in Java 8 and copy it and expand on it and see and look what it's doing underneath the covers there. That's the best way I can recommend you integrate your own streams into your own collections. So once we've got a stream, we can build up a recipe and operate on that data. So let's say we might think we have sort of words in there, these lists of string words in there. And some of them might be empty, so we want to filter out those empty words. So we just do s.length greater than 0. So anything that a string which is of length 0, we just chuck it away, like so. And then we simply say count like that. That's it. Now you might say, well, I can write that in a for loop, and you're right, you can. There's use for loops if you want to in this sense. You know, there's, if you want a more up-level description of what's going on and you want to process sequentially, for loops are still pretty good. We're not taking them away. I think this reads better in a certain sense. It sort of reads like what the behavior of the code is actually doing. But just let's just print this out just to prove it actually works. So remember that number, we have 68 words in our stream. So what is count actually composed of underneath? If we have a look at the actual implementation of count and go into our stream implementation, we see it's composed of two other operations, a map and a sum, like so. So the trick here to count is we map all the elements, all our words in the stream, and we just substitute each one with one, and then we count it all up. And that's a neat trick. You learn it once, and then you remember it later on like that. And you can do little transformations like that for your own stuff. So we can copy that code into our own substitute there just to see what's going on. So what we're doing is we're mapping from a stream which contains objects to a long stream. So if we look at this method here, it takes a function which takes a t and maps it to a long and then returns a long stream back out. We've introduced primitive streams as an optimization to avoid things like boxing. So when we get sum mapped along sum. So what's sum actually composed of? So let's have a look at the implementation in there. We see it's composed of a reduce. So now this might be familiar to you. Filter, map, reduce. That's a fundamental thing that's going on here. You can do it sequentially or you can do it in parallel. So I could actually do parallel on here and get the same result as before. 68 at before. But I'm actually running this in parallel. Now the question is, does that go any faster? How many people think that might go faster? Okay, how many people think that might go slower? Okay, the slow guys are the winners. So people are the winners here. This probably will not go fast. And we'll get into the reasons why that is the case. So the lesson here is don't start sprinkling parallel around on your streams, on every stream you do, because you might not get the performance boost. It's essentially an optimization. Okay, so instead of counting, what happens if we want to join all these words together instead? So we've got this list of strings. Let's create a paragraph out of that and join it all together. So let's stick with our reduce. We don't want the map anymore. But our end result, say we want a string back. We call it words, join words. Instead of dealing with numbers, what we're going to deal with is strings instead. So if we want to join them up, say we want to separate each word by space. Like so. So a little bit about reduce here. This is called, we call this a functional reduce. What it requires is a base value here and a reduction function. Now there's certain constraints on this base value and this reduction function. I'm not going to go into in detail. There's lots of other presentations out on the web that talk about this in more detail on the constraints. But the base value is essentially identity value. If you apply the empty string to a string, addition to it, you'll just get the same string back. That's an important property. And there's an important property of this that it must be associative. I have actually assertion code in here just to get that across if you want to look at it later on. We can't actually assert this at runtime. So you have to, if you want to do this and you want to make sure that these identity values and reduction functions are conformant, you have to write tests to make sure that they're conformant. Can anyone see anything wrong with that? Will it print out the words? Yes? Exactly. Let's have a look if that's the case here. So I forgot the safe harbor statement, so here it is, down below in my IDE for you to look at or read at your leisure. But yes, there is a rogue space there, because the first value that we reduce on, the A there, will be the empty string, and the first value in the stream will be B, which will be the word the, and we start off from that point. So we could, well, say, well, let's get rid of this first value. I don't want it. But we now got a problem, because if we don't have an initial value or a base value, if the stream is empty, what do? Should we return null? No, optional. Someone said that down below. The lights are a bit bright, so I can't exactly tell where the words are coming from. But so that's one of the reasons why we introduced optional here, is so that we can deal with something that is there or not there. And then we can print that out as well. So we should see some wrapping on optional there, but you notice the space goes away. So in optional now we can say get or else. What is it called? Or else get, like so, empty. Actually, I'm not getting the right. I don't know my own optional. There we go. Like so, and then we unpack the string out. So if we have a value there, get or else will return that, or otherwise it will return empty. So if we change this to say 100, like this, so there's no strings, no words greater than 100 characters in there, we should get the empty out instead. Like so. So is there anything wrong with that? Exactly, we're killing, the GC is going to have to work really hard underneath the covers in there. That's not particularly efficient. So reduce is great for simple value types like ints, longs, and stuff like that. It might be okay if you have persistent collections and that, but it might not, because it might, underneath the covers, sort of produce some sort of rather inefficient structural representation underneath that's holding all this data. So the right thing to do here is, rather than reduce, is to think collect instead. And collect is like a form of reduction that allows to use mutability underneath the covers. So that's what you should be using for strings and for lists and for stuff like that, is to look for collect. Don't naturally reach for reduce. Reduce is a more functional thing. For more purists, if you like, and can be useful. But collect is probably the thing you're going to be using more often. Like so, and that will work. And underneath the covers, this is using a string joiner. Okay, so here's a little fun example. Let's ROP13, the safe harbor statement. Anyone know what ROP13 is? Okay, so here's the stream version of how to ROP13 a list of a string. So we want our string as text. We want to convert it to characters. There's a method on string to get your code points as an int stream, like so. We map each character to a function that ROP13 is the character, and then we use the free arg form of collect using a string builder. And we want to create a new string builder. We give it the method to say how you add a code point to the string builder, and then we say how two string builders join together, and that's the key thing you need when you go parallel. And then we can print it out. So let's just see that works just for the fun of it. There we go. Which do you think is more understandable, the top one or the bottom one? Okay, that was a bit of fun. So let's go back to the slides. So let's start getting more into the meat of the presentation about going parallel. So I showed the stream there, the default sort of operation on a stream, or the default characteristic of a stream is sequential. But it can be made to go parallel using parallel, or on the collection classes, you'll see a thing called parallel stream as well. And it's really to get results faster, but you have to qualify that with a maybe. That's entirely, it's an optimization under the covers. If you play by the rules of the functions are essentially stateless. If you're using reduce, there's certain rules. If you're using a reducing function, it has to be associative, stuff like this. It's not a magic bullet, but it's going to, if you want to go parallel, it's going to make it a heck of a lot easier than programming, say, fork join tasks and stuff like that. It's inherently greedy. It'll always take more work, using as much CPUs as possible to get the work done in an attempt to get the result faster. So here is the algorithm at a very high level of what we do. The first stage, what we do is we split our sort of the elements that we're operating on into n separate leaves, and those leaves will cover approximately the same number of elements. So we have to split our problem up, and then we evaluate sequentially those leaves, each one of them, to produce L intermediate results, and then we merge those intermediate results up into one summary result. Now that's easy to explain in sequential steps like this. The challenge is to do all this concurrently. So some things might be splitting, while some things might be evaluating sequentially, while other things might be merging results together. And that is the mechanisms by we do this. We use fork join underneath the covers and something called counted completer tasks to track what's going on underneath the covers to do this all concurrently. So let's have a quick peek under the hood of what's going on in parallelism. So let me find my parallel streams, that's it. So here's a bit more complicated stream. I found there was a neat way of using streams to actually show what's going on underneath the covers when going parallel. So what I'm doing is I want to create a map whose keys are strings and whose values are a list of integer, where the keys are the thread that I'm operating on, and the list is the integers that have been operated on that thread. So let's say we create an int stream of range 0 to 127. We go parallel, we box it up, and then we collect by grouping by. And grouping by will say, map the integer that I'm operating on to the current thread's name, and then group all the integers on that same thread together in the list, and then print out the result. Using another nice little neat thing. If you're in Jose's presentation, you probably talked about these little neat methods all around the place in the JDK for reaching over a map with keys and values. So we can print that out. And that actually gives you an indication of what's going on under covers surprisingly well. So we can see we're using fork join. We've essentially got 7 fork join threads and 1 main thread. So we got a parallelism of 8. I have 8 cores on my system, so we've got a parallelism of 8. We're processing 128 numbers, and the granularity of processing is 4 numbers. So 4 divided by 128 is 32. We're splitting the problem up into 32 parts. So we're sort of over-provisioning our work. We could split it up into 8 parts, but we're deciding to split it up into 8 times 4 to over-provision to take into account thread scheduling effects and balancing effects and so forth like that. And we can see it's lumpy. We can see that some get 4, some get 32. We can see that it's not contiguous in a way. Each thread gets different bits of the work. So it's naturally sort of out of order, if you like, in what's going on underneath the covers. And we have to preserve order up above to make sure this non-determinism doesn't pop up above to you unless you actually want it. So if we run that again, we'll get a different result. And we'll get a different result like that. You know, it's inherently lumpy. This is not doing a lot of work again. Intuitive, this is very fast results. So we can actually create some work by hacking in a peak statement and using something called consume CPU that I copied from something called JMH, so be careful using this. It allows you to consume a bunch of work, just expressing an arbitrary number of tokens. I actually have to pass in, make the Lambda expression happy there. So I'm going to fake some work here. Let's see what happens. Now I have more work to do. You can see the threads are getting equal quantities of work to actually operate on. So you can see when we have less work to do, the balancing is actually not as good because it takes time to build up the threads, it takes time to schedule tasks and so forth like that. So the more work you do, the more chance you have of getting a speed up. Let's run that again just to show it should be approximately 16 with juggling there. So that's quite a good explanation of what's going on. And then I tried to sort of show this using ASCII diagrams, and it got a bit embarrassing, and I've done this before, so I'll show a better way of doing that later on. It's possible to limit parallelism if you want to. You can actually disable by setting a system property. This is unfortunately the only measure of control, publicly supported measure of control we have at the moment for this. We are considering other ways I will talk about later on. But that's the way you turn it off. And ironically, if you're in a web server environment, that's probably what you want to do. And I think app servers will do that by default initially. So it doesn't, because usually you size for throughput in your web service, and you don't want streams that may be marked parallel, perhaps when they validly or not, will just consume resources from processing requests. So you have to balance things quite carefully here. So you can limit it here. And now I'm going to show you something a little bit naughty in terms of this is not publicly supported, but if you really need to do it, you can hack in and control a pool programmatically by running a stream inside a fork join task. You can submit your stuff to a fork join pool that you created yourself and limit it that way. But that's not supported. So if you're desperate, do that. But don't say I told you so. That's is the rule of that. So hopefully that gave you a quick understanding of what's going on underneath the covers there, using streams itself. Okay. So when to use parallel streams? So I'm going to talk about two things. One about heuristics and measurement, and another about visualizing the stream pipelines rather than showing some hard-coded ASCII diagrams. I'm going to try to show you what's going on under covers, how things split up, and what sizes of things are when they operate on data and stuff like that. And it should give you a visual model of what's going on for certain things. So there's a very good document that was written by Doug Lee. This is the current home for it. We may find a better home, but this is the best one we found so far. I encourage you to read it and give us feedback and ask, was this helpful to you? Is there something we're missing here? Explanations and so forth. It's not a long read. In fact, it's up here. It's very accessible, and we'd like feedback on this if it's useful to you. So essentially, there's a minimum threshold by which you start getting equal to and better than sequential performance. And on current platforms, it's approximately about 100 microseconds. If your sequential version takes about 100 microseconds or more, then you've got a chance of getting a parallel speed up. And there's two ways you can work this out. First of all, you can estimate, or if in doubt, measure, and perhaps you should do both. But the estimate is quite a powerful one if you think of it of the back of the envelope thing. Who knows John Bentley's Programming Pearls book? You ever read this? If you haven't, I recommend you read it. It's a very nice book on programming. They call it in the small, but he comes up with... It talks about it here in this, I've linked to it in the presentation, but it comes up with a wonderful way, engineering tick, of back of the envelope calculations. And you can use it with a bunch of heuristics and a model to work out approximately whether my stream will have any benefit going parallel or not. And it's actually a nice engineering idea that we can apply to computer programming in general, but a lot of people apply to engineering. So if you haven't looked at Programming Pearls, I urge you to have a look, because it's actually quite enlightening inside, and it's a really good read by John Bentley. If you want to measure, I strongly recommend you use a tool called JMH. It's a micro benchmarking tool. It can be used for nano benchmarks, micro benchmarks, milli benchmarks, second benchmarks. It's not just for doing measuring stuff at really short time scales. It's very useful over a wide range of time scales. And it hides a lot of the interesting things that Hotspot tries to do to optimize, so you can get decent or consistent results out when you're measuring stuff. So what about the pipeline here? So if we have a collection, which I'm calling source, we've got it from somewhere, and we have a result produced by going parallel, and we have a map produced with two lambdas inside of them. Questions you can ask on your source is, does my stream source have good splitting characteristics? I'll get into some of those later. What is the size, n, of my source? Actually, I'll explain a bit about now. So an array list might have good splitting characteristics, because we know the size, we can index into the array very fast, whereas a linked list might not, because we have to traverse through it one by one by one by one. A small array list, like 10 elements, there might not be enough work to do. It depends on what's happening with the lambdas inside here. Whereas an array list with 1,000,000 elements, we have more work to crunch on. So another question you can ask is, what is the cost per element? What are my lambdas doing? Are they doing simple things like addition, or are they calculating probable primes using big integer? Or do my operations inject or remove elements or short circuit in the stream? Another good one, is there boxing or unboxing going on? Because if there is, you'll nosedive because GC will kick in. So the cost of the stream, approximately, is heuristic-wise, is n times q. And you can guesstimate q. You can even guesstimate it to lines of code in lambdas, which Doug talks about in his in the article. So a lambda with, say, just adding a number is one line. So q could be 1. So if n, this is approximate, but if n times q is greater than 10,000, you've got a good chance of getting a speed up on modern hardware. Doug says, well, if you're not brave enough, add another 0 or 2 onto that. So, it's fuzzy in that sense, but it's just to get you to think about this and to understand. So if n is very large, q can be small, but if n is small, q has to be larger. So Doug says this. Another way of saying all this is that using parallel when there's not enough computation might cost you 100 microseconds. And using it when justified could save you at least that, or possibly hours, depending on the computations you're doing. So here's an example I've shown before, which is comparing the parallel, the summation of an array of integers. For n is the number of size on the bottom, on the x-axis, and on the y-axis is speed up compared to a for loop. So I'm comparing a sequential and a parallel stream. As n gets larger, you can see that on a sequential stream, an int stream, it's still slower than a for loop. But at about 1,000 elements, we're on parity there. But you see the parallel stream is really slow. 100,000, it's just like all over, it's just dog slow. But as n starts to increase, we start to get a crossover point, which is not 10,000, but is in the boundaries of that fuzzy value there, where you get the crossover point. And then afterwards, we get to 1,000,000, 10 million, stuff like that. We start to get 2x. I measured this on a 2-core system. So that's for a low Q. If we go to a high Q, like probable primes, we need a lot less of those to get the parallel speed up. So after about 4 elements, we can get a parallel speed up of generating probable primes. Now, there's something strange about this graph. I have 2 cores on my system, and the parallel is saying I'm actually faster than my 2 cores because I'm above a 200%. What's going on there? It's as if the sequential is actually slower than 100% instead. And I don't quite know why that is, but someone suggested it might be that when I run these sequentially on one CPU, it's hitting thermal limits. So it's lowering the performance of the CPU. Perhaps that's true. I don't know. But that's one possible thing. When going parallel, we don't hit those limits. So it'd be interesting to know the exact reasons for that. It gets a bit mysterious. When you're measuring these things, especially on Intel, it's best to switch off the hyperthreading, because if you have hyperthreading on there, you'll get your results will be harder to compare, because strange things happen when you do hyperthreading. So you've got to be quite careful when measuring these things, especially for these types of results, if you want to get very good comparisons between sequential and parallel. Another way to look at this, other than heuristics, like the back of the envelope style thing, is to visualize stream pipelines. So I can actually render the representation of a parallel stream computation as a dot file. I can convert that dot file to SVG and view it in a browser. The code is online. You can actually look at how I've done this. So what we can do is we can have a collection source. We can convert it to a parallel stream. We can adapt that stage to monitor the splitting of the elements and the intermediate stage, and then we can peek at the elements coming through and correlate them between the two. So we have the source, the adapt, and the peak. So we can peak before the terminal to monitor the elements, output between the source and the intermediate stage. So we can have a source from a list, we can have a map filter, the intermediate stage, and then we can have a sum as the output. Another way of expressing this on the right-hand side is we can have an eval function that takes our stream source, takes a function from stream to stream for our intermediate operations with a bunch of lambdas, then takes a terminal operation that takes a stream as, say, like a reduction or something, and produces a result. So let's have a look at these examples in code. So for the purposes of this, I'm actually going to run these as JUnit tests, just because it's an actual convenient thing to do before and after operations on these things. It's just extremely convenient. So what I'm going to do is going to compare different sources, collections of integers, and I'm going to sum them up. I'm going to compare array list, hash set, and so forth like this, and see what the computation looks like visually. It's about 1 million elements. So we create an array list of content of 1 million elements, and we graph it. Essentially, this is our eval function here. We don't have any intermediate stage, it's just the identity function, and we have a reduction, which is taking in a 0 and integer sum, and there's a warning here that boxing is going on, okay? So the performance is going to be a bit all over the place. But for the purpose of what we want to show, that's fine. And there's a bunch of stuff here doing a before class. I'm actually setting my parallelism to a limited amount. I'll show that in a bit more. And afterwards, I'm actually opening up in the browser, like so. So just JUnit is very convenient. So I can actually, let's actually run this. Let's have a look at the output. So here we go in my browser here. Let's try and scale that down a bit first of all. So if you see, this is a computation tree coming out. I'm listening in to how it's splitting up. So at the top here, we're talking about an array list here. So we know its size at the top. We also know its size when we split. So these dark gray boxes are saying, I know my size. And the size of the elements here is approximately 1 million. And at these points when I split, they're divided by 2 each side. And we show the thread and the time it actually occurred on relative to the first one. And then we split again, and then we split again, and then we stop. We stop when we reach a certain size threshold, when we say, well, we might as well go sequential now, there's no point splitting, because it will just create unnecessary work. So we're splitting, so we've got a parallelism of 2 here. So there should be 8 tasks at the bottom here. If we actually go into here and remove the setting of the system property to reduce the parallelism and run that again. We'll see a much bigger tree. That's the one with I showed with the streams underneath the covers with the sort of the 32 tasks coming along here. So we do a lot more splitting. So let me just change that back before I forget. And let's have a look more closely at the array list. So array list, we know our size all the way down to the bottom of splitting. That's an important characteristic. If we know our size, we can optimize much better than if we don't know our size. And at the bottom, these round circles, they represent the sort of traversal state of performing a reduction operation. So we can see we get a number of elements in, we get a number of elements out, and we have the duration it took to actually do that, which is not a realistic measure of performance here because we haven't run it a number of times, we haven't waited for hotspot to kick in and so forth for that, so take that with a pinch of salt. But the important thing here, array list splits very well, very evenly, and very balanced. We get an equal amount of work at each point, so array list is great for parallel operations. Let's have a look at a different class. Let's have a look at hash set. Do you think hash set would be the same as array list? No. Let's have a look. So hash set looks a bit different. Hash set, we know our size at the top, But when we split it, we don't know the size anymore. We only have an estimate. And the reason is we have a bucket where we map from key to list of values that map to the hash to the same key, essentially like that. So we have a bucket in there. So what we know our size at the top. We will split the bucket in half, and we say if we've got a good key distribution algorithm, we would expect approximately half of the elements to be in the top bit of the bucket and approximately half to be in the bottom bit of the bucket. And then you split again, and you split half. So I'm representing the size here as an approximate size because we don't know it exactly. Know it exactly, we would have to traverse, and traverse would create more work, and there'd be no point in doing that. So we get the same type of tree shape coming out, but we don't know what the exact sizes are at the bottom. And in actual fact, what we're getting at the bottom here is, I'll zoom in, I think it's easier, is, well, the left-hand side here is full, and the right-hand side is empty. What the heck is going on here? This doesn't look right. This is not very evenly distributed. What it's actually showing is a bug in the hash map hashing. When it hashes the keys, there's actually a bug here. The size of the table in the hash set we're talking about, the map, will be twice the size of the number of elements we have. And the hash code of an integer is the integer itself. And the hash code of hash map is, let's have a look what hash map is doing in there. This is the hashing. It's taking the hash code, XORing it with the hash code again shifted down by 16 bits. So I've got 1 million elements in there. It's taking the top 4 bits and just monkeying around with the bottom 4 bits and not really doing a lot. So my numbers are going to be all boxed to the right hand side, to the left hand side of my list. So we need to improve our hashing algorithm. So it showed a bug in the system. You shouldn't expect that behavior with strings in that, but it's interesting. When I first looked at this, I thought that can't be right. It was like, there's something going on here. It's either me or the system. And I usually blame me first, because it's usually me. So, but you can see how we're getting double the amount in here. It should be even distributed. We don't know the size. So at each point here, we have to do a little bit of extra work, more work than we would have had to done in ArrayList. So HashSet is not as good as ArrayList in terms of its splitting capabilities or its abilities to split out and partition work. Because the key distribution algorithm may be okay, but it's going to be a bit lumpy in places. So let's have a look at a linked list. Do you think linked list will be the same as same shape as before? How many think it will be the same shape?
As what? As the array list or the hash?
As in the same struct, split nice and evenly in terms of 2 by 2 by 2 by 2. You think it'll be the same? Who thinks it'll be the same? Who thinks it'll be different? You, right. Okay. Let's see. So let's run that. Oh. So let's just keep zooming out, zooming out, zooming out, zooming out, and it goes on and on and on and on. Linked list is a poor choice to use for splitting. That's the moral of this story here. Because a linked list, we can only iterate through it one by one. We can't index it directly. There's no O1 lookup of the elements, if you like. So the only way we can derive parallelism from this is copying a prefix of the list into an array and then operating on that array. And essentially we have an arithmetic progression. So we copy 124 elements off the list, operate on that, and then the next task, we copy 248, 372, and we gradually increase that in size over time. So we're sort of trying to balance out a sort of small and high queue, because we don't know what it is. We're trying to balance it out over time, get more work. So there's a limited amount of parallelism we can extract from this. So if the cost of copying the elements from the list into the array is higher than actually operating on the elements into the array, you're not going to get any speed up. So you have to be very careful with a linked list like this. It just goes on and on and on. And in fact, this caused a bit of problems initially because it would create runaway TAF. It would create out-of-memory errors because we were just running away, splitting. So we had to be quite careful about how we do the splitting between threads. And if you look at this carefully, you'll notice a little pattern of switching threads. And there's a good reason to do that, so we don't run away creating too many resources that we can't actually operate on fast enough. So let's take another example of an iterator. Actually, just back to this point, we know what the linked list size is. So when we split it, when we take elements out, we still know what its size is. Because we know all its size, that's all good, but we still get poor splitting characteristics because of it. So if we have an iterator of known size, will we get the same shape as the linked list? Just show that quickly. So I'm creating a stream of an iterator instead and saying what its size is. We get the same type of shape coming out. Iterators are a poor choice as well as linked lists for very similar reasons. If we don't know the iterator's size at all, we'll see a slightly different version. N is question mark. We haven't got a clue how many elements are in this iterator. So we still pull what we can off it and still keep on going, and it's still the same shape. But if we have a smaller iterator of known size with small content instead, not 1,000,000 elements, but a smaller number of elements, we'll start to see a little bit of a different shape. And the reason is our threshold for splitting is a lot lower than before. To stop splitting is a lot lower. So when we split off 1,000 elements and get to 5112, we'll start operating on that. So we get a kind of sort of lumpy-ish shape. So the important thing here is size is an important characteristic to optimize. If we don't know its size, even for a small iterator, there's not much we can do. We get that same shape again, coming back. So let's look at another example. We added a method to files called files.lines, and you give it a path, and it will return you a stream of lines as strings coming in. So it's a very convenient method. So what do you think the shape of this will be? Same as before? Unfortunately, it is at the moment. It's going to be the same as before. But there's ways we can optimize that. We should be able to do better than that. We should be able to mem-map the file in. We know its size, and we can use that as an approximation to work out and split that in half and work out where line boundaries are. But we haven't implemented that yet. And in fact, Maurice Naftalan has written a Lambda book where he talks about that, and I'm trying to get him to contribute that code back. I keep having to hassle him. So we can do better under those circumstances. There's a lot of improvements to some of the implementations we can make over time. Let's take a quick look at range. What do you think of the shape of an int stream.range from 0 to 1,000,000 elements would be? Same as linked list, same as array list? Let's have a look what that is. It's the same as array list. So ranges are nice as well. So array list good, range good, hash set okay, linked list bad, iterator bad. That's the essential thing here. But now you've got a visual picture in your head of what linked list or iterator does. You can see the amount of extra work it has to do. Okay. I've got 60 minutes. I'll go back to the slides, and if I have time, I'll come back to some more of these with intermediates and terminals, because I want to talk a bit about the futures. And I'll see if there's questions, and we can carry on if we have a bit more time. So a bit about boxing. Boxing is obviously a problem at the moment. We'd love to get rid of boxing if we could. It makes the GC work harder. There's all sorts of pointer chasing and unaligned layout blows the caches. Brian talked about this a lot about Project Valhalla and stuff like this. And it can affect sequential and parallel processing, and the drop in performance can be astonishing. It really can, either sequentially or in parallel. That's why we have the int long double streams to avoid the boxing. So if you have an int array and compared with an integer array, the integers of that integer array are spread out in memory. They're all over the place. And that chasing blows the caches because it's not predictable, and it affects the performance, because when you get a piece of data from memory, you'll get other pieces of data which are close to it. But when you're traversing an integer array and unpacking the boxes, the data's not where you want it to be. And it gets worse when you have pairs. And it goes, and so there's more pointer chasing going on. And in fact, I can quickly show that using something called Java Object Layout Tool, which is actually pretty neat tool. Another tool written by Alexei Shipalev, or JMH was written by Alexei Shipalev and others now. But this object layout tool allows you to look at the layout of objects in memory as they're represented in hotspot. And I've created a very simple example showing an integer array and what happens after the integer array over a period of time, what happens when GC kicks in. So I'm going to just run this and hope it shows quickly what I want. So what I'm basically doing, I'm looping through here, creating an array and creating integers in that array. And then I'm looping through again and saying, does the layout of that array change? If so, print it out. And I'm using Java Object Layout to do that. So initially, if you see that, things are kind of nicely aligned. You can see I have the array created first, and I have the integers in there, and it all follows through. Prefetch will work quite nicely there. I won't blow my caches out. Okay, there'll be extra data related to object headers and stuff. But once GC starts kicking in, it spreads out and gets all mixed up. And that's where your performance will drop off the cliff there. And that's why we want value types. That's why we want to line things nicely in memory so we don't get the performance drop. So avoid boxing sequentially or in parallel if you're worried about performance. It might not be a performance issue for you. Okay, that was a quick sideline into that. Okay, so future and near term. We need a better parallel resource control strategy. As I showed you, we only have parallel. You can't say how much parallelism you want. There's no way to control this. What we need is a way to say how much parallelism you want without actually explicitly binding to a number of cores, because where you run your code might be different. We need a strategy perhaps to say, I'm doing I/O or something like this, because the fork join pool at the moment is not so good at dealing with I/O-based tests that block. So we need to, that can be an understatement. So we need the strategies for that to allow that to happen, because you can use RxJava and stuff like that, but at least we should try and evolve streams to make it a bit more friendly. So if you want to process HTTP requests coming in, you can say you're doing a parallel I/O strategy, and that should be a reasonable thing to do. We want to improve a bunch of splitting implementations. Files.lines I talked about before. There's some things related to limit that I need to improve on. And in fact, limit is extremely hard to parallelize under the covers because it is inherently stateful. I don't think I'm going to be able to show it in terms of visualization, but there's reasons why we were kind of reluctant to think about this initially because of the cost it has. And this relates to more operations that we haven't added yet, called take while and skip while. These are very common things people want on streams, and we didn't add them initially because we had a certain budget for our implementation. And these, like limit, if we want to get them to work reasonably performant in some parallel situations, they take some time to tune and implement. Mostly they limit will often have to buffer. These will often have to buffer too to get the work done. So we might use more memory parallel-wise, but sequentially they have good value. And I think we should add these in 9 time frame. There's also certain things we can add more stream-based sources, like on Matcher. We have it on the pattern for regex, but we don't have it on Matcher at the moment. Stuff like this. If you can think of other places where we should be adding streams, please tell us. We'd like to pepper them around. We have peppered them around the JDK already, but there's probably other places we can add them. There's helper methods we could add. We could add stream to optional. At the moment, it's quite difficult to use optional with the stream flat map. I don't know if you've ever tried that, but it's awkward. So we could turn optional into a stream. So if an optional has an element, it would be a stream of one element, and if an optional doesn't have one, it would be empty. We can add stream of nullable as well to help with these things. Little sugars here. This is we have to be careful adding methods to optional because everyone has their own pet methods they want to add to optional, and it starts ballooning out of control and just goes crazy. So I'm setting a really high bar to what goes into optional, and I think this meets the bar and has usefulness in other ways that it can be consumed in streams. In the longer term, we could do a lot more. As we talked about in the Java 9 panel, Java 8, 9 and beyond panel, we have this tension between what we can do now and what we can do in the future. And I see what's coming in the future, and I'm saying, well, if we do certain things now with streams, it's not going to be as good as what we can do, and then we're stuck with it going forward, and we'll still have to make it better somehow going forward. So the right thing to do is hold off on some things and wait. So in the near term, we could develop a pluggable SPI for operations. We have a limited set of operations on the streams. We could have an SPI to plug in for streams, but we can do so much better job later on going forward than we can do now, that I'm reluctant to actually do something about this today. I have a prototype there, but I think we should wait on this. There's another thing we could add, which is a by stream, which is to make it easier to use streams with maps. Streams with maps are kind of ugly today. We've used them. We could add a by stream. This might have more value, but if we have tuples in the future, do we still need a by stream, perhaps? Or a map stream, perhaps? Associated with more map function, perhaps that makes sense. In the distant horizon, we have value types and extending generics over value types. We have int stream today. We added that because we need the performance of int stream. But in the future, can we have stream of int? Let me see if I talk about that. Yes. So int stream, can we make int stream extend stream of int? Have we done something stupid today that will make us regret it in the future? I certainly hope not. But if we could do that, that would be really, really good. And what if we can have tuples of streams of int and so forth like this? And then we can do nice things with zip and so forth like that we haven't actually added. Every time we add a function, we have to consider, do we want ints, longs, and doubles to be supported as well as references? And it just, this explosion, combination explosion starts to happen. We have to be very careful what we do. But when we get generics over values and stuff like that, we can limit this explosion. And we can do such a better job. So there's this tension between what we do now, or do we wait until to do something better? So that's a proper safe harbor statement there. So I can go back to some of the graphs, or I can take some questions. I've got 7 minutes for questions.
So I haven't internalized the whole optional API yet, but is there a method asset, and if not, could you use that? Because then you could say asset.stream.
Sorry, I couldn't quite hear the question. Can you speak a bit louder?
Does the optional type have a method asset that would either return an empty or a singleton set?
No.
Well, that would be another alternative, because then you could call .stream on that.
You could do that too. I think stream is better because it has less it will create less churn on memory and so forth. So the question was, should we have an as set on optional instead of a stream? Yes, we could. I prefer stream. And the reason why it works better with flat map, it's more concise with flat map, because flat map accepts the stream coming in. And then you can convert that stream to a set or to whatever you wanted to using the collect or something like that. So I think that has more value. Any further questions? No more questions? Yes?
You show the system property to control the Z2. Then the set away the
Sorry, can you repeat the question?
you use the system property to control the fork join tool.
Yes.
So locally,
You want a programmatic way to control the fork join pool for streams. Is that what you're asking? Yes. At the moment, there isn't a way. We have to. This is what I'm talking about, the parallel resource control strategy here. We need a way to control the parallelism of the fork join pool, but not in the simple way you might expect of passing in a number of parallelism directly into here. We need a more abstract way of specifying that information. But yes, we need to do something about that. Okay. Any other questions? I have 5 minutes for more questions. Take the opportunity now. No more? I'm having trouble seeing. Yes, at the back there.
Where would you put in something like lazy collections? You have a generator to generate all the elements, but you don't want to store them all at once.
Yes,
all the tuples of 5 elements of some whatever. Yeah.
So you're talking about lazy collections. So if you would have a filter method on list that returns a new list, but it's lazy. Is that what you're getting at?
For example, or I have a generator.
Yes.
I just have something like a an iterator or generator. Okay.
Oh, yes, there are mechanisms to say iterate on a stream. If you look at the streams method here, there are a bunch of factory methods, if I can actually find them. I can't actually find them. There are a bunch of factory methods saying iterate, generate, stuff like this. So the generate method will say you pass it a constant and it will generate it infinitely if you wanted to. The iterate method will take an initial value in a function and will keep iterating on that to generate a stream as well. So you can there are those packaged in today, and you can create your own underneath the covers if you look how we've integrated those types of things into the system. So you can create your own generators if you want to as well, cycles and stuff like this. We kept it to quite a minimum, but it's not quite as expressive as you might see, say, in the closure API or something like that. Okay, I have 3 minutes left. One more question? No, I think we can go 3 minutes early. Thank you very much. Oh, sorry, there's one more question. Sorry.
With the introduction of value types, will that affect significantly Java memory model specification or not?
Hopefully not. I don't think it will. There might be. We might have to say something about atomic operations on value types, and it might be if you have a large value type, you just might have to give up on atomic operations and say you have to use a lock. If you have a small value type which fits into 64 bits or something like that, or is amenable to hardware instructions or something like that, you might be able to do atomic ops. But I don't think we have to get into that detail with the Java memory model. So I hope it's actually going to be minimal in terms of what has to be expressed. So the memory model is being updated in 9, and I hope we don't have to significantly revisit it for the future with value types. That's my hope. Okay, I think I'm done. Okay, thank you very much.